vector space. Definition of vector space. Let V be a non-empty set and its elements are called vectors. The elements of V, that is vector space, are called vectors. But just we say the elements of V as a vector. Vectors means in physics, in vector means quantity having direction and magnitude. This is not the definition of this vector. Just the element of vector space are called vectors. It does not mean the quantity having magnitude and direction. Just the element of vector space are called vectors in this paper. So now V is a non-empty set on which two operations called sum or addition and is denoted by usually plus sign, and the scalar multiplication denoted by dot or just space without dot, that is the scalar multiplication. So it's the two operations called sum or addition and scalar multiplication defined on this vector space V. Okay, so these two operations are defined on V. So its definitions are given. This sum or addition is not your usual addition. That what is your usual addition? For example, 2 plus 3 is 5. This is usual addition. But this sum or addition is denoted by this plus sign. But its definition is specifically given in the that example. That is, this definition of addition is depend on that example, or what is given in that example. It is not your usual addition. And this scalar multiplication, for example, 2 into 3 is 6, is your usual scalar multiplication. But this scalar multiplication is not your usual scalar multiplication. It depend on that example. Okay, so that let V be the vector space, V be the non-empty set on which the two operations sum and scalar multiplication are defined. Then V with these two operations, just say V, or we write V comma plus comma dot, means scalar multiplication, addition, and V. All these three, with these three, that is V with these two operations, is called a vector space or linear space. Vector space is also called linear space. So just V, we say V or V plus dot is called vector space or linear space over R. What is the meaning of over R? Means the scalars comes from this R. That is, the scalars comes from the set of real numbers, and is also called a real vector space. This is called real vector space. So vector space over R, if the following 10 axioms are satisfied by the elements of V. So what is the structure of vector space? Vector space is a non-empty set with these two operations and with these 10 axioms. So when the set with these two axioms, with these two operations satisfies these 10 axioms, then that set is called vector space. So vector space means one set, two operations, and 10 conditions. What is the vector space? Vector space means one set, non-empty set, two operations, and 10 axioms. Aggregately, this structure is called a vector space. So what are the type 10 axioms? First two are called closure axioms. The second, the next four are called addition axioms, and the next four are called scalar multiplication axioms. So these are the total 10 axioms. So the first axiom, the first two closure axioms. First one is what? U bar plus V bar belongs to V for all U bar and V bar belongs to V. That is, V is closed for addition. Another way we say that V is closed for addition. And what is the meaning? Very simple meaning, that addition of every two elements of V, addition of every two elements of V belongs to V, present in V. If this happens, then we say the first property is satisfied. This is denoted by notation C1. So what is C1? U bar plus V bar. What is the notation for elements of V? Say U, V, W, these are the notations for the elements of capital V, vector space. And what is this bar? Just indicate that it is an element of vector space. We write the bar or write arrow at the top of this notation. V bar or V raised to V arrow, right here, arrow. So in some books, the notation is just U and V without arrow and without a bar. So we can use either bar or arrow at the top, or just U and V and W are the elements of this vector space V. So this bar is not necessary, not compulsory. We can write bar just in order to distinguish the vector and scalar. That is the elements of vector space and the elements of this R. So to separate the elements of R and the elements of V, we have to write this bar only. It is not a usual vector, that is the quantity having magnitude and direction. This is not the definition of this vector. Vector means just the element of vector space. So this bar is not compulsory. We can use bar or arrow at the top, or without we can write just U and V and W are the elements of V. So this is the first property, that V is close for addition. That is, addition of every two elements of V belongs to V, present in V. So when this property we say false or dissatisfied for the set, if you take suppose the set of uh, natural numbers, then what happen? Addition of every two natural number is again natural number. While if you take the set, suppose this set V contains the element 1 to 100. Suppose the set V contains the elements 1 to 100, all the natural numbers like from 1 to 100, that is 1, 2, 3, 4, 5 up to 100. Then this set is not close for addition, because if we take the two elements, suppose from that set, suppose 50 and 51, or 50 and 52, suppose we take 50 and 52, then what is the addition of 50 and 52? It is 102, and it is not the element of V, because V contains the elements from 1 to 100. So if we take any finite subset of a natural number set, then it is then for that set this property dissatisfied. And so the set 1 to 100 of natural numbers is not vector space, but because first property is dissatisfied. So when set is vector space, if set satisfies these 10 properties, but when the set is not vector space, any set V is not vector space, if any one of the out of these 10 property fails, any one out of these 10 property fails for the set, then we say the set is not vector space. So set of natural numbers satisfies the first property, that is close for addition. But if we take any subset, any finite subset of natural number, for example set 1 to 100, then it does not, then the first property is dissatisfied for that set, and that therefore the subset of natural number is not vector space, any subset of natural number, any finite subset of natural number. Similarly, what is the second property? K U bar belongs to V for all U bar belongs to V and for any scalar K. K is scalar means K is the element of R, and this property is satisfied by the set, then we say that set is close for scalar multiplication. So what is the property? If you take any element of V and if you take any scalar and if their multiplication belongs to V, then we say it's satisfied. This property is satisfied for that set. When we just said this property fails, we do a counter example. That is, if you take set of natural numbers, suppose n is the V, this capital V is equal to capital N, set of natural numbers. That is, the elements contains the element, the set contains the element 1, 2, 3 up to infinity. Okay, and this property is dissatisfied for that set. Why this property fails for the set of natural numbers? If we take K as 1/2, suppose K as 1/2, and U bar, that is the element of set of V means natural number, as a 3, then 1/2 into 3 is 3/2, and 3/2 does not belongs to N, capital N, and therefore for set of natural numbers this property fails. C2 fails. C1 true for hold for natural numbers, set of natural numbers, but the second property fails for set of natural numbers, and therefore set of natural numbers, that is capital N, that contains the element 1, 2, 3 dash 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 up to infinity, this set is not vector space because the second property fails for the set of natural numbers. That is, if you take any scalar and any element of n, capital N, their multiplication does not belongs to n. If you take k as 1/2 and u bar, that is, suppose u bar, that is set of element of capital N as 4, then 1/2 into 4 is 2. Then 2 is a natural number. That is, for these two elements, it satisfied, the property is satisfied. But when we say this property is satisfied, if it is true for every element of that set V and for any scalar k, that is, if we take scalar 1/2 and the element of set of natural numbers as a 3, then 1/2 into 3 is 3/2, and 3/2 does not belongs to n, capital N, natural number set. And therefore set of natural number is again not a vector space. The first property is satisfied for the set of natural numbers. Addition of every two natural number is natural number, but the second property fails for the set of natural number, and obviously set of natural number is not a vector space. Okay, so the next two properties, next four properties are called addition axiom. So what is the first axiom? A1, that is this is third property of the vector space. U bar plus V bar is equal to V bar plus U bar, and it's called commutative law, commutative property. That is, the addition is commutative. Then second property of addition axiom is U plus V bar, U bar plus V bar plus W bar is equal to U bar plus V bar plus W bar. For all U bar, V bar, W bar belongs to V, and it's called associative or called associative law. The third one is existence of 0. There exists a 0 bar in V. It is the just notation 0 bar. What is this? Is called 0 vector, and it is not a usual 0, your usual 0. But what is its property? U bar plus 0 bar is U bar for all U bar belongs to V. So it is necessary that there exists an element 0 in that vector space. If this 0 does not exist in V, then V is not vector space. So this is the existence of 0 vector. 0 vector must be exist in the vector space in that set. If the 0 vector does not exist in the set, then we say it is not vector space. So which element is called 0 vector, and what is its notation? 0 bar is its notation. And what is 0 bar? U bar plus 0 bar is equal to U bar. If the element satisfies this property, it's called 0 vector, and for all U bar belongs to V. So if we add this 0 vector in every vector, in any vector, then we have the same vector. So such an element exists in the set V. Then next is existence of negative vector. For each U bar, for each vector U bar belongs to V, there must exist the vector minus U bar in V, called negative vector of U bar, such that U bar plus minus U bar is 0 bar. So what is this property? If the vector exists in the set, in the vector space, then its negative must be exist in the same set. For example, if you take set of natural numbers, then in the set of natural number 0 does not exist. So this property E3 is also dissatisfied for the set of natural number. This fourth property is also dissatisfied for the set of natural numbers, because what is the negative of 2 is minus 2. Minus 2 does not exist in the set of natural numbers. So what is this property? If the element exists in the vector space V, then its negative must exist in the same vector space. So negative of every element of V exists in V. So what is the negative? The addition of that two element is 0 vector. Okay, so then these two are called negative of each other. So if the element exists, then its negative must be exist in the set V. So this is the existence of negative vector. So the next four properties are called scalar multiplication properties. K U bar plus V bar is equal to K U bar plus K V bar for all U bar and V bar belongs to V, and for any scalar K. Then K plus L, K and L are scalars, and U bar is the vector element of V. So K plus L U bar is K U bar plus L U bar, and then K L U bar is equal to K L U bar. Again, K and L are scalars, means elements of set R, real numbers. K and L are real numbers, and U bar belongs to V is the vector. And 1 into U bar, right? 1 dot U bar or 1 into U bar is equal to U bar. So this K dot either write k dot u bar plus v bar. Here k dot u bar or k dot v bar. So dot is not necessary here. Dot means scalar multiplication. So just this empty space means scalar multiplication. Okay, and this plus means, this plus sign is what? Is the addition, sum or addition, is the notation for addition. So either write this dot notation or don't write this dot notation. Right, this property in the another format we can write k dot u bar plus v bar is equal to k dot u bar plus k dot v bar, or just write like this. So these are the 10 axioms. Some in some examples these properties maybe fails. This last property we observe 1 into u bar is u bar, but what is the 1 into u bar? This is not your usual multiplication. Usually we know that if we multiply the element by 1 we have the same answer, but this 1 into u bar, this multiplication is not our usual multiplication. That's why in some example 1 into u bar is not equal to u bar. We have this in some examples. So this property maybe fails in some examples. So if all these 10 properties are satisfied for the set, then we say that set is a vector space. So what is vector space? Vector space is a non-empty set and 2 operations and 10 conditions. So if the set with these 2 operations satisfies these 10 axioms, 10 properties, then we say that set is a vector space. Otherwise, if one of the any out of these 10 property, one property fails for the set, then we say the set is not vector space. So the first example of vector space, obviously the set of natural number is not vector space. Set of integer is not vector space. Why set of integer is not vector space? Again, the C2 property fails for set of integers. That is, if you take k as 1/2 and u bar as 3, then again 1/2 into 3 bar, 3 is the element of the set of integers. Then 1/2 into 3 is 3/2 is not integer, and therefore the second property fails for in set of natural numbers, set of integers, and therefore set of natural numbers, set of integer are not vector spaces. The set of real numbers R is a vector space under the 2 operations, usual addition and usual scalar multiplication. What are the usual addition of real number? For example, if you take real number 3 and 2, then its addition is 3 plus 2 is 5. So set of real number is a vector space under these 2 operations, usual addition and usual scalar multiplication. What is usual scalar multiplication? We know that 2 into 3 is 6, 4 into 2 is 8. This is usual scalar multiplication. So under these 2 operations, usual addition and usual scalar multiplication, the set of real numbers is a vector space. That is, the set of real numbers satisfies all these 10 properties. We will check the first property, then the addition of 2 real number is real number. Scalar multiplication of 2 real number is again real number. Addition of real number is commutative. Addition of real number is associative. 0 element exists in the vector in the set of real number. That is, your usual 0 is the 0. Each for each vector, its negative also exists in the R. That is, the negative of real number is a real number. Then these properties are very obvious. We know that scalar multiplication distribute over addition is called distributive law. From left and right we have this. This is left distributive law, this is right distributive law, and we know that all this is the associative property of multiplication of real number. And 1 into 5 is 5. We know that 1 into 5 is 5, for example. So all these 10 properties are satisfied for the set of real numbers under the usual addition and usual scalar multiplication, and therefore this capital R with usual addition and usual scalar multiplication is a vector space. The next example, V is equal to R square. What is this? R square means R cross R, or is the set of all order pairs of real numbers. Okay, for example, or we can write V is equal to R square is equal to set of order pair X, Y, such that X and Y belongs to R. In the place of X, Y, we can also use the notation U1, U2 or V1, V2, U1, U2 or V1, V2, U1 and U2 belongs to R. So we can write order pair that is the set of all order pairs with real entries. So these x and y are real numbers. So this is the set of all order pairs. And what is the definition of addition? So for u bar as xy and v bar as x dash y dash, or we can take u bar as x1 y1, v bar as x2 y2. These are the just notation. So or u bar as u1 u2, v bar as v1 v2 belongs to R square. Define u bar plus v bar is equal to xy plus x dash y dash is x plus x dash comma y plus y dash. That is the addition of corresponding components coordinates, x's coordinate and y, addition of yy coordinate. This is the usual addition of order pair. And then k is any scalar. Suppose k is any scalar, then k into u bar is k into xy, order pair xy is kx ky. This is again the usual scalar multiplication in R square. And with respect to these two operations, this v or R square is a vector space. So show that v is equal to R square is a vector space with respect to these two operations. So we just remember that this R square with usual addition and usual scalar multiplication is a vector space. This proof of this example is not important as far as the exam concerned, but for our interest we can prove the give the proof of this example, a solution of this example. This is the solution of this example. As far as the exam concerned, this solution of this example is not very important. So now we have to show this R square is a vector space, means we have to show 10 properties. So first property A1. So for that we take this u as xy, v as x dash y dash, w as x double dash y double dash, be any three vectors in R square. Then now we have to show first property, that addition of every two element of R square exist in R square. So u bar plus v bar, u bar and v bar are any two elements of R square. So what is u bar plus v bar? xy plus x dash y dash is x plus x dash y plus y dash. What is this? This is by using the definition of sum in R2. It is new. It is not your usual definition. It is given in the example. What is the addition of the two vectors? We take the addition of two vectors like this. So here the addition is this x plus x dash, y plus y dash by definition of sum in R2. This sum, how we have to take this sum? It is given in the example. So we have to take the sum give as far as the given in example. Don't use your usual definition of addition or multiplication, scalar multiplication. What is given in the example? So you do the addition what is given in the example. So this is the addition, and obviously this is order pair, and x and y, x dash y and y dash all are real numbers. Addition of two real number is real number. So x plus x dash is real number, y plus y dash is real number, and obviously therefore this x plus, therefore what do we have? X plus x dash comma y plus y dash belongs to R square. So this is the first property. Addition of u bar plus v bar belongs to R square. And then k u bar, take u bar as xy and k as any scalar, then k u bar is kxy, is kx ky, and this is again element of R2. And therefore the first two properties C1 and C2 satisfied for R2. Write that two properties, then write these properties. The first two property, write C1 first and then C2, and then write A1. So A1 is what? U bar plus V bar is this, and we know that addition of two real number is commutative. X plus x dash, we can write x dash plus x, y plus y dash as y dash plus y, and again reuse the definition of sum in R2. We have x dash y dash plus xy, and then v plus u. Then u bar plus v bar is equal to v bar plus u bar. Right? Arrow at the top or bar at the top. U bar v bar. Just write bar. Don't write this arrow. So then u bar plus v bar plus w bar is this x y plus x dash y dash plus x double dash y double dash. Then x plus x dash y plus y dash is the addition, and then x dash plus y double dash. We have this, and the addition of real number is associative. We can write x plus x dash plus x double dash as x plus x dash plus x double dash, like this. Y plus y dash plus y double dash, we can write y plus y dash plus y double dash. The associative sum in R. We know that 2 plus 3 plus 4 We can write 2 plus 3 plus 4 as 2 plus 3 first, add 2 plus 3, then it is 5 plus 4, 7. Or 2 plus 2, 3 plus 4, and then add 1. Okay. So 2 plus 3 plus 4, we have the answer 8 in both way. So addition of or sum of real number is associative. And then again we have x y plus x dash plus x double dash y plus y double dash, and then the addition of this is what? X dash y dash plus x double dash y dash, that is u bar plus v bar plus w bar. So we have this property a2, u bar plus v bar plus w bar is u bar plus v bar plus w bar. Then as 0 belongs to R, what is the 0? 0 0, right here 0 bar. What is the 0 bar? Order pair 0 0 exists in R2. So 0 vector exists in. What is the property of 0? If you add 0 0 in u bar, then we have the answer u bar. U bar is xy, so we have the answer u bar. So 0 vector exists in R2. We denote it by 0 bar. And if you take u bar as xy in any element, then it's minus u bar minus x minus y exists in R2. Is the element of R2, because x and y are real number, then minus x minus y also real number. And what is their addition is 0 vector, 0 0. And therefore negative of every element of R2 exists in R2. Then M1 property, k plus k into u bar plus v bar as this. So we have k u bar plus v bar is k u bar plus k v bar. Similarly, if we take k plus l u bar, k and l are scalars, u bar as xy, then we have this, and then we have k u bar plus l u bar. So and then k in k l u bar is k l xy, u bar means xy, and then we have this, and we have k l u bar. Okay, take just k common, because multiplication of real number is associative. So we have this. Then 1 into u bar 1 into xy is 1x 1y by using definition of scalar multiplication given in the example, and it is equal to xy. So 1 u bar is u bar, and therefore all the 10 properties are satisfied by the R2 and the operations given, the two operations given sum and scalar multiplication, and therefore R2 is a vector space under the given two operations. Similarly, we can write the same problem in another notation. V is equal to R2 is equal to U1 U2. What is the U bar now? U1 U2. U1 U2 belongs to R. Then addition is defined like this. Again the same. And for instead of K notation, here the notation is alpha for scalar. Alpha U bar is alpha U1, alpha U2. That is the same definition, usual addition of order pairs and usual scalar multiplication. Then show that V is a vector space. Again, show the first C1, C2, A1, A2, all these 10 properties. So U bar as U1, U2, V bar as V1, V2, W is what? W bar, right? W bar as W1, W2, the 3 element, and alpha and beta are scalars. Then U bar plus V bar is just U1 order pair U1 plus V1, comma U2 plus V2, and is the element of V or R2, because it is an order pair. This is an order pair, alpha U1, alpha U2. And so first two properties C1 and C2 satisfied for V. Similarly, A1, A2, A3, A4, M1, M2, M3, and M4, all these 10 properties are satisfied for the set R2, and therefore R2 is a vector space. It's called real vector space. Okay, real vector space with respect to the given two operations. So both the problems are same, just the difference is the for notation. So take a R2 as a set of order pair xy or set of order pair u1 u2. So this is the same problem. Then in this way R3 is a vector space, Rn is a vector space. R3 is what? Set of order set of 3 tuples x y z, such that x y z belongs to R, set of 3 tuples. And again the addition of the two vectors, suppose u bar is x y z, u v bar is x dash y dash z dash, then their addition is like this: x plus x dash, y plus y dash, z plus z dash, 3 tuple. And k u bar is this: kx, ky, kz for any scalar k. Then V is equal to R3 is a vector space under these two operations. Similarly, if you take Rn, what is Rn? It is write R raised to n, but read it as Rn, R raised to n. So Rn is what? set of n tuples x1 x2 dash 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 xn x1 x2 xn belongs to R. Set of n tuples, all n tuples, and the addition of these two n tuples is like this: addition of corresponding element x1 plus y1, x2 plus y2, xn plus yn, and ku bar is this: k x1 x2 xn is k x1 comma k x2 comma k xn for scalar k. Then V is a vector space with respect to these two operations. These are the usual addition of two n tuples, usual scalar multiplication. So under these two operations, V is a vector space. So R square, R cube, R raised to 4, R raised to n, all are the vector spaces with respect to usual addition and usual scalar multiplication. So we can define R raised to n like this: u1, u2, un. Instead of this xy, x1, x2, xn, we can use the notation u1, u2, un. So it is just difference between notation. R raised to n is set of all n tuples u1, u2, un, such that ui means u1, u2, un belongs to R. So again, the addition is given, scalar multiplication. Instead of k, here the notation is alpha. So V is a vector space. So we can also give the proof like this. All the example, V is equal to R2. So this is the proof for V is equal to R2. Similarly, we can prove R3, R raised to 3 is a vector space. R raised to 4 is a vector space. R raised to n is a vector space. So if I have to write the proof of this example, R raised to 3 or R raised to n. So follow this proof. So in similar manner, we can show that R raised to 3, R raised to n are vector spaces. So this is the next example, fourth number example of vector space. So we will see the remaining examples of vector space in the next lecture.